Okay, so so today we're gonna kind of go to the next part of the course. So what we have seen so far, which is divide and conquer, dynamic programming, and amortized analysis. This is kind of a classical stuff that has been developed maybe mainly in like 50 years ago, something like that, like in the 80s or even 70s. So today it's going to be a bit newer, which is about randomized algorithm. Okay. So in the next few weeks, the hope is that you'll see more and more the power of using randomization in computing. Yeah. And so let me start with this first quiz. Just imagine that you have array of size n, and each of the array contains either 0 or 1. Each entry is just 1 or 0. Now there are two cases. Either most of the entries here are 1, 90% of them are 1, or 90% of them are 0s. Okay, and that's the two cases. And what we want to know is what is the fastest deterministic algorithm that can figure out which case holds. So now, one trivial way is just, okay, scan the whole array, spend n time, and you know which case it is. So I want to claim that actually you need something like linear number of query as well. Can you tell me why? Why do we need linear number of queries? Yeah.
2n over 10 plus 1. Because you need to, in either case, there's at least n over 10 of the lesser one. So if you have 2n over 10, then you're guaranteed basically at least after you query 2n over 10 plus 1 times, it's guaranteed that at least you'll have at least n over 10 zeros or n over 10 ones. So you can know what.
Yeah, good. I understand you. Yeah. So you said that as long as you query let's say just 2n over 10, that's not enough. You need to n 2n over 10 plus 1. Let me try to tell you even simpler argument. Let's say I just make n over 10 entries that I query. I query just this much, right? It can be the case that I only see 0. I'm so unlucky, and all I see are just zeros. I just query this, got 0, and then the algorithm said the next one is this. It's always 0. Next one is 0 again. And then maybe but I still don't know the rest. And with this, it can still be either of the two cases, right? I only say it's n over 10 zeros. It can still be the two cases. It can be the case that everything else is 1, or most of them are 0. Yeah. So the point is you need linear number of queries, and yeah, you might want to try to see exactly why, as you said, you need actually, if you want a precise value, you need exactly 2n over 10 plus 1. That's enough, and less than that, you cannot distinguish the two cases. Yeah.
Oh, never mind. Sorry.
Okay.
Yeah.
Okay. Good. So yeah, you can do it in linear number of query for deterministic algorithm. So now let me ask you one thing. If you want just a randomized algorithm that is correct with 90%, how many query do you need? Yeah, what's the algorithm?
You just sample any element of the array and return that element.
Yeah.
Before you guess which element is most common.
Yeah, good. Yeah, exactly. So just one query. Just look at the random cell, query that, and return whatever it is. Okay. Why this is good? Because let's say there are 90% of ones. Then if you take the random cell with 90%, you will return one, right? Because 90% of them are one. If most of them are zero, with like 90% you get zero. So that's the power of randomness. You just reduce from linear to one, right? And so to talk more about this, like we need some more basic probability background. So like I'm just gonna kind of flash through this concept quite quickly because I assume that you kind of have seen it before. So like the setting is that there's gonna be a set of outcomes, and for each outcome, sigma in omega, each outcome have some probability associated with it. Yeah. So probability of sigma. And the random variables is nothing but just a function that map outcome to a number, a real number. And expectation of random variable is just kind of the average over this value of the random variable. So basically, it's like a weighted average of the value of x when the weighted is like the weight is weighted by the probability. So now the important property of expectation is that it satisfies linearity of expectation. It satisfies this thing. Like expectation of the sum is a sum of expectation. You know this, and I want to note that the important thing is that this is always true. Like it doesn't matter if xi are related or not. Doesn't matter if xi are independent. This is just true. And we're gonna need basic bound like union bound, which says that suppose you have event e1 up to en, the probability that union of ei exists. So like sum of the event happen, the union that sum of the event happen is at most sum of the probability of each event. Okay. And next, Markov bound, which is a way to say that to say that okay, your random variable shouldn't be deviated too much from the expectation. So it says that the probability that x deviated from the expectation by a factor of t is at most 1 over t. And equivalent way to write this is just x greater than the probability that x is more than t, at least t, is at most expectation of x over t. And this is true. Note that this is true only for non-negative random variable. Okay, so that is just like some basic thing. So let's try to do some exercise. Suppose you have 10 dice. And let me say that let t count the number of times that you roll the same value twice in a row. Just you have rolled like 10 dice 10 times, and you want to count how many times you roll the same value twice in a row. Okay. So what is the expectation of t, right? Well, maybe it's, yeah, let me just go through it quickly. I think, so, okay. One way to do this is just create some indicator random variable, mi. This thing just say that this is an indicator random variable, which says that if the event here is true, then the random variable is 1, otherwise it's 0. Okay. So I justify mi here, and mi is true if mi is 1 if like the ith minus 1 and ith row match. So can you tell me what the expectation of mi? Yeah.
1/6.
Say again.
1/6.
1/6. Yeah. Thanks. And why do we consider this mi at all? This is just because t is nothing but the sum of mi from m2 up to m10, right? And so now, by linearity of expectation, now we can just compute the expectation of t. You have this, but this is just a sum of expectation, and each mi here is just 1/6. So you sum them up, you get 3/2. Okay, so just for a quick check, what's the can you say that this thing is smaller than 1? The probability that t is at least 2. Can you try to bound this thing? Actually, how should we bound it?
Markov.
Yeah, we can use Markov, right? By Markov bound, we get that t is at least 2. This probability is at most expectation of t over 2. So that's like just 3/4. So this is less than 1. Okay, so how about next exercise? Like you've seen this thing, like n balls and n bins, throw it uniformly. Now let me ask what's the expectation of empty bins, right? Well, we can set mi again to be yeah, the way to go is kind of just to look at in some indicator random variable that you know how to analyze, and then so in this case it's mi, which is indicator whether bin I is empty, and this is good to look at because expectation of number of empty bin is just a sum of expectation of each mi. And yeah, what is the expectation of each mi? Anyone?
One minus 1 over n all to the n.
Yeah. Why is that? 1 minus 1 over n to the n. Why is that?
Because when you throw each ball, it lands in a bin besides mi with probability n minus 1 over n.
Yeah. And then, yeah, this is the probability that you miss the ith bin, but you throw n balls. So the probability that you miss n times is just this thing to the n. Good. And now, so you have this, and with this, we can compute the expected number of empty bins. Just sum this thing up, right? So you get this thing times n. And how do you simplify this this expression? Well, this thing is at most 1 over e. Okay. And the way to see this is that for any, this is a useful inequality that I want you to remember. 1 plus x is at most e to the x for any x. So it means what? It means that this thing is e to the minus 1 over n, and everything here over to the n. So this is just 1 over e. Make sense? Good. Yeah. So note this, it's gonna be useful whenever you work with, many times in your calculation. 1 plus x is close to e to the x. And the reason why this is true is just like you can think that this is like kind of interchangeable even when x is small. And the formal proof is this part is true for every x, but for another direction, e to the x is also less than at most 1 plus x squared. But when x is at most 1. But this thing you should think this thing is so tiny when x is small, right? X squared is so like when x is less than 1, x squared is much less than x. So think of this as something tiny, which means that if you ignore this, then e to the x is just the same as 1 plus x. And once you kind of put this into your heart, then like you can see very quickly that, okay, when you see this thing, this is just the same as like 1 plus epsilon, because both of them is something like e to the epsilon. When you see this is just this, like they are kind of the same here because both of them is e to the epsilon times k. Like it's just kind of a quick way to calculate stuff without worrying too much. Okay. So now, so we have seen Markov bound. It's a way to say that the random variable shouldn't deviate too much from the expectation. Now we're going to look at Chernoff bound, which is way stronger. But to talk about this, we need to talk about independence, right? And two random variables, x and y, are independent if like the probability that x has outcome x, even if you know something about y, is the same as the probability that x has outcome x. In other words, like having knowledge, any knowledge about y, doesn't change anything about x. Like it's very intuitive what it means to be independent, like, and it's formalized here. And now, if x and y are independent, you get like a nice equality here too, that expectation of the product xy is a product of expectation. And so note that this is important that x and y are independent, right? Because, for example, otherwise, if x is like a random number 0, 1, and if you take y to be 1 minus x, like a flip bit of x, then what you know is that, okay, expectation of x is half, expectation of y is also half, but expectation of x times y, this is always 0, right? Because one of them must always be 0. So this equality is just not true when things are independent. But when like the random variable are independent, let's say like x1 up to xk are independent and is between 0, 1, then good things happen. Like you can say something strong about the sum of this xi. So let me say that let's say that x is a sum of this xi, and let mu be the expectation of x. Okay. So when x is a sum of random things which are independent, yeah, when x is a sum of independent stuff, then we have something super strong. That is the probability that x deviate from its expectation by this, like deviate from expectation by like multiplicatively by like by delta factor, right? That is like exponentially small. Yeah. So like this is just a way to say that x is at least this thing mu or x at most this thing times mu, right? So actually, if you just use Markov bound, here you would just get that this is at most 1 over 1 over 1 plus delta, just something weak. But here, you get something like e to the something that is exponential. Okay, like this is just kind of exponentially small. Okay. So it says that the probability that x deviate from mu either by more than mu by like 1 plus delta or less than mu by 1 minus delta factor, that's so small. Okay. But note again that this works only when x is a sum of independent random variables. And then, so this is the case when like the deviation is small. Like, but for large deviation, you also have this. That is, x minus mu is more than, like, it is more than expectation by lambda. That's exponentially small in lambda. So, like the point is that you don't need to kind of remember like precise bound here, but you should say that like the thing that you should remember is this thing is exponentially small when x is a sum of independent thing. And there are actually many other variants of Chernoff bound. You can look up in this thing, for example. But the message is that the sum of independent random things are basically quite predictable. You can know with very high probability that it's going to be very close to the expectation. Yeah. So massive randomness is kind of not that random. Okay. So let's try to use Chernoff bound question. Okay. Let's try to use Chernoff bound in some application, right? Let's see. Oh, and you can have a look at the proof of Chernoff bound, like plenty in the internet. But I will not prove it for you. Let's see how to use it though. So suppose that you have n numbers that are unsorted. And what I need is I want some number x whose rank is something like close to median. Like the rank is somewhere here. Like if suppose this is after you sorted, you get suppose that you sort the array, the numbers, and you get this. Then this is like the rank n over 3 and 2n over 3. You want x somewhere here in the green area. Okay. And you want this x with high probability, like 1 minus delta when you think of delta as something small. So we see how to do this in linear time. Even like the median, we can get a median in linear time, right? Even deterministically. But now what we want is we want a constant time algorithm. We want to do it in constant time instead of linear. Any random idea you want to suggest what we should do? How to do this? How to solve this in constant time? So suppose that I just want to get this guy with probability at least 1/3. What we should do? Yeah.
You can pick 3 numbers and pick the middle one, and then think that'll give it to you with probability greater than or equal to 1/3?
Yeah, if this is just 1/3, just pick one guy at random.
Oh, okay.
That would work already. But you have a good intuition that if actually you pick 3 guys and now choose the middle guy among these 3, now it should even be closer to, like, it should be like in this range with even higher probability, better than 1/3. Okay. So we can try to like analyze that, but that's kind of a good intuition. And the idea is, okay, let's just do something like that. Instead of 3 guys, let's pick some large constant number of number. Just pick like k many guys where k is like some this number. Okay, just sample each of them independently, and then just return the median of this set. So make total sense, but why this is enough? Like we just need to calculate that. Okay, we can get like this probability where the number of things that the size of your sample is just this much. Okay, and to see here, we just kind of gonna use Chernoff bound. So the proof is here. Like, suppose that I say that, okay, for each sample I say that xi tiny is an indicator that my sample I is tiny. Like, it goes to this part. Like si is here. And let x tiny just count the number of 2 tiny sample. Do the same for like x huge, xi huge, indicate whether your sample I is on the this side, and x huge count this huge sample. Okay. And now observe that the algorithm is going to be wrong. Actually, maybe right. Let me write. The algorithm is going to be right if and only if x tiny is less than k/2, and this thing is also less than k/2. Right? Because if you sample and you sample k guys, and like you sample a bunch, but there are less than k/2 guys here, less than k/2 guys here, then it means that your median of the sample must be in the green area. Right? So as long as the tiny guys and the huge guy are not too big, less than k/2, then you're good. No matter what, the median is going to be in the green area. Okay. So now what I will show is just that. And so the algorithm is wrong if x tiny and x huge is big, bigger than k/2. But I'm going to show that both events here happen with very small probability. So to analyze this, we just say that, okay, we know that for each I, xi tiny, the expectation is 1/3. Because that's the probability that you go to the tiny part. It's just 1/3. So in expectation, x tiny is k/3. Okay. So expectation is like k/3, but the algorithm is bad if x tiny is much more than k/3. It's more than k/2. Right? So that's like and we don't expect this. And how to show this formally? We have that. We're just gonna use Chernoff bound. And note that we can use Chernoff bound because x tiny is a sum of xi tiny, and each xi tiny are independent. They are independent, like each sample are independent from each other. So we can have that, okay, the probability that the x tiny is more than k over 2 is just the same thing as saying that x tiny is more than the expectation by 3 over 2, because the expectation here is k over 3. And now you plug in the Chernoff bound, right? There should be minus here. And then so x tiny is something like k over 3, and k is something like, I just choose the constant to be large enough so that I don't need to think much about it. This thing over 3. Okay, so this is something like exponential of minus log of 1 over delta. So that's going to be something like much less than delta. It should be something even like delta to the 10 or something, which is less than delta over 100. Are you with me? Okay. Good. So,
Sorry.
yeah.
Why is delta? Is that delta negative 10 or? Sorry.
What is?
Kind of confused by the notation. It's delta to the 10 also?
Yeah, delta to the 10. So because at the end, when you kind of, okay, this should look like this. When you write this, when you simplify this, you should get like x of maybe 10 log this thing. And that's just delta to the 10. And delta to the 10 is much less than delta over 100. Let's say that I assume that delta is at most half, then that's going to be true. So now we have that, okay, the probability that x tiny is bigger, much bigger than the expectation is so tiny. You're going to get the same thing, the same conclusion for x huge. So both of them is more than x over 2 with probability less than delta over 100. So now we are done by union bound. So the algorithm is going to be wrong with probability like delta over 50. Okay, question? Okay, good. So you can try to do this at home, just make sure that you understand. Instead, let me say that now we want like the x to be very close to the median. Like the rank is something like this. So instead of n over 3 and 2n over 3, you have epsilon here. Okay. And you can check that just by, like, you can still get a constant time algorithm where the size of your sample now, there is this like epsilon over 2 in the dependency of your size of the size of your sample, and it's gonna work too. You can try this at home. And also in the quiz in the beginning, we saw that, okay, to distinguish the two cases of the array, just by one query, you can make it correct with 90% probability. So now if I want to boost my correctness probability to arbitrarily close to 1, just 1 minus delta, all you need to do is just return the majority of these many samples. So like log over 1 over delta, log of 1 over delta. Cool. So you can try this. So this is going to be simple, but let me try to look at more complicated things. So let's look at this process where suppose that you have a path of n nodes of length n. So n plus 1 node maybe. This is a path. It's a discrete path. And then suppose that what I do is just I will just split a path at a random position. Okay. And when I split, then I keep a larger half. And then I just repeat this until my path have length 1. So keep splitting at random, take the larger side, split again until the path have length 1. There is just one node in the path. So the path, yeah. This is the number of nodes, yeah. Good. So now what I want to count is the total length of all paths that we have kept in all rounds. Sum the length of path that we have kept. Okay. So like in the beginning. So first of all, can you tell me what's the worst case length that we can get?
Half of the length of the path.
Um,
Or per split or like total?
No, in total, what's it like the worst case total length of the path that we have seen so far?
N?
More than that, actually. So just to make sure you understand, I have the path of length n. The worst case, the thing that can be as bad as possible is that I split here.
The longest possible length or the smallest?
The longest, yeah, sorry, yeah.
Then should be like n squared.
Yeah, like n square. Like each time you just reduce the size of the path by 1 in the worst case. So the sum of the total length of the path is something like n square. And now, what is the expected length of the total length? What is the total length in expectation? It might not be clear, but I actually you have seen something like this before in previous class, in way before,
Is it 4/3 n?
something like that maybe. So, but it's gonna be linear. Yeah. And the reason is that if you think about this, so try to recall the randomized quick select algorithm. You know, when you the one that try to choose median in a random way. You start with an array, you choose a random pivot, and then you go to the left or right side with depending on your pivot. And when we analyze that algorithm, right, we choose a pivot and we say that, okay, let's analyze the time when we even go to we always recurse on the largest side. And even when we analyze that algorithm, even when we analyze that worst process, go to the largest side all the time, that is linear in expectation. And that analysis it's just the same thing as this process, where the path is just the numbers, and you choose a random pivot, and then you split, and then you go to the larger side. Right? So the total length of all the paths you kept so far is really just kind of the same thing as the running time of quick select, randomized quick select. So you have that in worst case is n squared. In expectation, this is worst case. Worst case. And it's in expectation. Expectation. But what I'm going to show is that you get n log n. with high probability. So actually, like the running time of the quick select algorithm is linear in expectation, but with very high probability. It's not going to be more than n log n. Okay. So if this connection to quick select is not clear, you can think about this at home. But for now, let's try to analyze this thing for this game. Good. So let's see why how to even analyze this, right? So how should we start? Let me start by define pi to be the path at round I. And it's going to be enough for me to show this. That is, I want to say that the probability that the path at round h, where h is something like log n, this probability, like the probability that the path at round h have length more than 1, still has more than 1 node. That's tiny. Why this is enough? Because if I know that I'm gonna stop after h round, let's say that I start with the whole path, and if I'm gonna stop at h round where h is like log n, then the total length of each path in each round is at most n anyway, and there are h many rounds because once this happens, that once the length is 1, then I stop. So the total length, even in the worst case here, it's just n log n. So all I need to show is that I should stop with high probability after like 10,000 log n rounds. That's enough. So how should we do this? Well, so what I'm gonna do is that let me say that xi is an indicator that pi, the path after round I, shrink the size by quite a bit, by 9/10 factor. If the path shrink by a constant factor, then I say that xi is 1. So it's like a good round. This round is good because it shrink the path quite a lot. And let x count the number of good rounds. Then what you get here is that you can see that the length, if the path have size more than 1, after h round, the total number of good rounds up to round h actually must be at most log base 10/9. Why is that? Yeah.
Otherwise, you've had like enough good rounds that the algorithm should stop earlier.
Yeah, good. So in each good round, it shrinks the path a lot, right? But we know that the algorithm doesn't stop yet. So the number of good rounds must be small. Good. Because if the number of good rounds is more than this, the path would have shrunk to 1 already. Okay. But now, if this is the case, then x must be small. But I want to show that actually the expectation of x is large. Why is that? This is because for each round, the probability that you have a good round is actually is 8/10 because if this is a path and this is like top and bottom 1/10 fraction of the path, if you choose to split somewhere here, which is of size 8/10, if you choose to split the path somewhere here, it's going to be good. So expectation of xi is at least 8/10. And so when you sum this over h round, so expectation of x is 8h/10. Right? But you see that I choose h here to be large enough. Like h is just some large enough constant times log n. So this is more than 2x. More than 2 times this thing, which is more than x. More than 2x. This is just, yeah, h is just big enough, so this is more than 2x. So it means that if the algorithm doesn't stop, then now x must be less than half of expectation of x. So what do we do next? All we do is, okay, this shouldn't happen because x is much less than expectation. So we use Chernoff bound. We have that xi are independent. So Chernoff bound is valid. We have that if this happened, then this must happen. So the probability that this thing happened is at most the probability that this thing happened. But this, the probability of this, that x deviates from expectation by a lot, it must be like it's exponentially small. So just plug in Chernoff bound, and then you get this thing. Okay. Good. Question about calculation?
Sorry, so the first inequality, why is 2 times log n? Like,
I mean, this is just way bigger than this thing. I just choose 2 because so that this is 2 here. Okay. All right. Good. So now, yeah. So we have that the total length is n log n with very high probability, and try to convince yourself that this means that randomized quick select takes at most n log n times with high probability. There is going to be some homework related to this. So another thing that I just want to show you quickly, and you try to do this at home, is imagine like some simple process where you are on number line starting with 0, and there are 1, 2, and 3, and so on. And you start here, and on each day you're gonna go left or go right with like equals probability. So in expectation, like, so xi is like xi minus 1 plus or minus 1 with equal probability. So for each I, you know that expectation of xi is just 0. In expectation, they are at 0. Right? Because in expectation, you don't move, actually. You go left and go right with the same probability. But in the worst case, xi can be as big, like xn can be as big as n in the worst case. But we can say that with 99% probability, xn is something like root n. And with very high probability, it's like a root n times log n, root of n log n. And you can try to show this, and the keyword is Hofding bound. It's just some variant of Chernoff. Try this at home. But this is kind of some behavior that is good to know. Like when you do random walk in 2D, as the end step, you're kind of close to root n, not n. Like it's still kind of not super concentrated, but still within root n here. So, okay. So now, what I'm going to do next is we're going to look at randomized data structure. And the problem that we look at is dictionary. So we have seen this many times. Like dictionary is like a data structure that maintains a set of keys, n keys. It can handle a bunch of operations, delete, insert, predecessor, successor. And you can implement this using balanced binary search tree. It takes n space, and every operation takes log n in the worst case. Can we do this better? That's the question. And what I want to do is to improve log n to constant. But to do that, we're gonna go to the more restricted setting. So I will just design an algorithm that can handle only update and look up, no predecessor and successor. Moreover, I'm gonna assume that the universe is bounded. Okay, so the keys are numbers up to number u for universe. Do you think of u as like maybe like 20 or 200 bit string, like URL or something? So u is still bounded, but it's still huge, right? You can be as big as 2 to 200. It's still huge, like much way bigger than the size of your input, but it's bounded. Okay, so this model is still very useful. So one trivial way to solve this problem is, okay, let's allocate the array of size u. Then everything is constant time. But obviously this is bad because the space is u. You just don't have space this big. You want the space to be proportional to your input, n, not u. So we're gonna solve this using hashing with chaining, and the algorithm is simple. So suppose that you have n keys. So now let me, instead of allocate array of size u, I just gonna allocate array of size n. M is n. But now each entry in the array is a list. Okay. And what I'm gonna assume for now, we're gonna remove this letter, this assumption, is that I'm gonna assume that I have access to a completely random function h that map each thing in the universe randomly to a random number in M. I assume that I have this thing. Okay, I assume even that I can evaluate this function in constant time. So anything related to this function, I assume that I have it and it's fast for now. But if I have this random function, then the algorithm to implement this dictionary is simple. When I want to insert x, I just add x to the list at which position, or at the list in h of x position h of x. If I want to delete, just look at this position, the list at h of x, remove it from the list. To look up, just look at x in the list here. So it looks like this. Like if I have m is 8, I allocate array of size 8, and I have n keys, 6 key here, and then if somehow my random functions map this guy, and this guy, they are all mapped to 1, right? So when I insert them, I just gonna put it into this list. When I delete them, just delete from this list, and so on. Very simple structure, assuming that I have a random function. So let's try to analyze this data structure. Okay, so you can see that the time to delete insert a query X is just proportion to the size of the list at position h of X, plus the time to evaluate the function, but we assume for now that it's constant. But then we just need to analyze the size of this list. Okay. So what's the size? So, well, we have that. Let's look at the expectation of the size of this list. Right? The randomness is over h. So that's going to be 1, because you know that h is going to be in this list. So that's 1. But then you need to sum over all y, not in x. Sum over all y in the set which is not x. And the probability that h of y is h of x. Right. Okay. So what is this? So does this make sense? At least like this is equals to the expectation of this thing is just this expectation of the size of the list. Okay. So can you tell me what is this? Given that h is random,
1 over however many things in the original list.
so there are many things like I have a choice for you. There is 1 over n. N is the size of your set. 1 over m. M here is a size of array. Which one?
Over n.
So it's 1 over m because h is a function from u to m, right? So it maps each guy into random number in m. So whatever this guy is, like when you fix h of x, whatever it is, when y is different from x, the probability that it's gonna map at the same value here is just 1 over m, because there are m choices for h of y. Okay. So that is. So what is this? This is 1 plus this is this sum, and this thing is 1 over m, and you sum over s minus 1, right? So this is just 1 minus s is just n, and this is m, but m is n. We set m to be n, so this is just O of 1. So we get that the time for everything is in expectation constant. Super simple, but yeah, it is. Oh, okay, this is just you get, and so you get linear space. And expected time for each operation is constant, except that we assume that you have a random function. So let's try to remove this assumption. So first of all, why do we want to remove question?
Yeah, so if you don't know n beforehand, can you allocate like some array and then keep doubling it? Would that still be like amortized out of 1? Is that
There is a way to make it work, yeah. But here I kind of assume that I know n, yeah, right. But let's say that I know that if I choose like m to be, let's say 100n, and okay, I don't know. Okay, how should I say this? Let's say that I assume I know n for now, and it's not too hard to make it work for like when you don't know n. Yeah. Okay. So why do we want to remove this assumption at all? Like why do we want to avoid completely random function? And the reason is that completely random function is just inefficient. So how to see this? So let's say that I set all to be like, all is like a set of family of all function. It contains all function from that map U to M. So how many set are in, how many functions are in this set all? Yeah. Yeah, M to the U. Why?
You choose an element in the codomain for each of the U elements in the domain.
Exactly. So it's M to the U because for each guy in the universe, you have M choices. So you have U many guys, each guy have M choices, so you get M to the U choice. So now, if I ask you how many functions in this set has this like can be represented using these many bits. Okay. So if you have like X bit, no matter what, you can represent 2 to the X many different things, no matter what, because you have X bit of strings. You can represent 2 to the X different things. Diff things. So if you have this many bits, it can represent this many functions, 2 to that many bits. But that's like just like a square root of m to the u, which is much less than m to the u. But it means what? It means that if you take a random guy, random function in this set, well, only tiny of them, only tiny amount of function have at most this many bits of representation. So most of them will take this many bits of representation. Right? Only tiny of them can be represented succinctly. Most of them can be need this large representation. And that thing is this is u times log n. So just to represent this random function, you take space something like u. That's as bad as like a trivial implementation that takes space u. Just to represent the function itself, that takes too much space. Okay. So it's just too bad if you use completely random function. So the goal now is to come up with much smaller family H instead of all. You want a family H, not all. Such that if you sample a random function in this family, within this family, then H takes more space and time to evaluate. And also H, but we still want that H still behave like a random function, a completely random function. So that's the goal. So Does the goal make sense? Like that? Like, question? Okay. So when I said that it behaves like H ideal, the completely random guy, what do I mean by that? So the behavior of ideal random function is there are many things that seems useful. First of all, very natural is to ask for uniformity. That is for any keys x and any position I, we want that the probability that h of x is I is uniform, so 1 over m. So each key maps to each position in a uniform way. Okay, that's one property. Another property that seems useful is small collision. That is for each different key, for each pair of different key x and y, the probability that they map to the same place is small, 1 over m at most. There is a stronger one actually called pairwise independent. That is for any different key and position I and j, the probability that x is mapped to I and y is mapped to j is 1 over m squared. Okay. You can actually say that this thing implies both of this. You can try to look at this, why is this the case. But there is even stronger one, which is k-wise independent. It says that, okay, if you have, instead of two keys, if you have k keys and k position, the probability that xj is mapped to the position ij for each of these k keys is 1 over m to the k. So you can say that like the way this one is strongest, n-wise independent is just everything is independent, and this thing implies k-wise, and it implies 2-wise independent, and 2-wise independent implies both of this. So try to convince this at home why this is the case, but pretty simple from the definition. But you see, a completely random function satisfies this strongest guy. But what do we need in our hashing with chaining? The property that we need is only here, way below here. Only small collision, not above there. Okay. So why is that? Because if you look back into the analysis, right? We only have this thing. We bound this. And we just want this to be small, 1 over m. So that's exactly the property of small collision that we need. It's not 2-wise independent, it's not n-wise independent, it's just small collision, this weak property that we need. Okay. So because we need for something super weak here, we should hope for that there should be small family that like any function in that family still satisfy this small collision property, and this everything is efficient. So that's exactly what we're gonna do. We want hashing family with small collision property.
I'm a little bit confused about like what kind of function would be k-wise independent but not n-wise independent. Like I don't understand how that could be possible.
So there is such a function. Maybe we talk about this maybe later or even in homework. I'm not sure. Yeah. But each of these, like in this hierarchy, you have like some example where it satisfies the one thing but not the thing above. Yeah. Good question, though. Yeah. So what I want to show, like, well, let's give the definition first. We said that a family H, a family of functions that map U to M, has small collision property if for like a different key, when you sample H, a function from this family, then these two, like they collide with probability at most 1 over m. When I say that H has a small collision property, another name for it is also said that H is universal. People call this before, like we don't need to understand why. There is a reason for this, but it's a weird reason. So this might be a better name for it. Just say that H has small collision property. And note again that this property, when I say this property is a property of a family H. Okay, it's not of one particular function. I said that H have this property if whenever you sample a function from this family, then the probability that the two key collide is small. So I want to construct efficient families that have this property. So let's do that. One example is, suppose for now that U is prime. It's not too hard to assume this. And now let me define a function HA mapping U to M like this. H of A map, given X, I just multiply X to A, and then I mod P, and then I mod M. That's a function H of A. And my family is just this collection of HA. My family have HA from when A is 1 up to P minus 1. So you see that, okay, for any function in H, clearly, like H of A takes constant space to store because you just need to know what is A. And it takes constant time to evaluate as well. Just multiply and mod in constant time. All I need to show is that this H, the family, has small collision property. So why is that? Well, we need some algebra fact. That is, if I fix any number z which is non-zero, for any c and I which is between 1 and p minus 1, this is c, this is I. The probability that once you choose A from this set randomly, the probability that A times Z mod P is I. This is exactly 1 over P minus 1. So, and this is where we need that P is a prime. The reason behind this is algebra, like I'm not sure, like the multiplicative group of a finite field is cyclic. That's why this is true. Yeah.
Yeah, so the order, there's like exactly P minus 1 elements in that. So it's like obviously 1 over P minus 1 if you like know that fact.
Yeah. Good. Right. That might be easier way to prove this, yeah.
Yeah, or like if you have like prime P, then any number from P is coprime, so there's an inverse.
Good. Yeah. Anyway, if we just assume this, and we just need to prove that when X and Y are different, then when you choose A at random, in other way, like you choose H of A randomly from the family, right? Then this probability is at most 1 over M. And okay, so let me do the math. Maybe let me just go through the math quickly because it's not that important. So let's analyze this event when these are the same, right? So if these two are the same, it means that this whole expression, which is the definition of this guy, this whole expression, when this is x and the whole expression here are the same. This is just the definition of HA of x, HA of y. And these two are the same if these two things here is a multiple of m. They are the same mod m. So it means that the difference of this is a multiple of m. Okay. So it means that the probability that x and y collide under HA means that this thing is a multiple of m. It cannot be 0 because x and y are different. This whole thing cannot be 0. So if it is multiple of m, it must be non-zero, which is the first thing is m, and then 2m, up to something that is still multiple of m, but still less than at most m. So this is this thing. But each of this is the same as one particular guys in this set with probability 1 over p minus 1 by the fact above. It equals each of them here with this probability, but there are just this many guys in the set here. By union bound, you multiply it. And that's at most 1 over m. Just some math. But it means what? It means that this simple family satisfies small collision property. Actually, it's not even satisfy uniformity. Because you know that, why is that actually? Because if you put 0, if x is 0, it always maps to 0, right? So it doesn't map 0 uniformly at random, it maps 0 to 0 always. So it's not even satisfy uniformity, so not even here, here, but it's to satisfy this thing. But this is all we need, because now let's try to do hashing with chaining without this assumption that we have random function. Let's say I just sample h from the family with small collision property, and each of these h like I take small space and constant time to evaluate. So just redo the analysis, right? We get that the time to evaluate h is constant, and this thing is still true because h have small collision property. So the expected time for everything is still constant. And that's the way usually the way how we design hashing algorithm. We just start with the scheme, analyze that algorithm or scheme, assuming that you have a complete random function just for simplicity, and then show that, okay, even simpler hashing family suffice, is enough. In this case, we show that, okay, in this algorithm, hashing with chaining, we can just sample a function from a family that has only this property, and we are done. So today we get to this. Instead of log n, we get constant in expectation. So next time we're gonna remove this expectation, and at the end we're gonna go to cuckoo hashing with constant worst case query time and space, and it's also work well in practice. All right, then see you next time.